Use the table to answer the following questions. What is the distance traveled at 4 seconds? How long does it take to travel 52 feet? What is the distance traveled from 2 seconds to 6 seconds? Let's look at that one together. From 2 to 6 seconds, we went from 13 to 39. Well, 39 minus 13 would be 26 feet during that time. Answer the remaining questions for your warm-up. This is a digital lesson, so if it's available to you, feel free to open up and follow along on your computer or just follow along with the video. So we have two tables for each car. You can see car A, it travels 1 second and 44 feet, but car B follows a different pattern here. We can say that car A travels at a constant rate of speed because each second it travels 44 feet. However, car B does not travel at a constant speed. It is actually picking up speed as it goes. The more time that passes, the more distance it travels. How does the table for car A show a constant speed? The constant of proportionality is 44 feet per second. If we divide 44 by 1, we get 44. 88 divided by 2 is 44. So we have a constant of proportionality here. Let t represent the number of seconds it takes to travel d feet. Write an equation that relates the distance the car travels to the time it takes. This is car A. So the distance is 44 times the time that it takes. So we'll use our equation now to answer these questions. In a half of a second, 0.5 times 44, because we're replacing or substituting 0.5 into the equation, would give us 22 feet. If we substitute 1.5 into the equation, we should have 66 feet. If we replace the time with 2.5, 44 times 2.5 is 110. And then 3.5 times 44 is 154 feet. Average speed. It says, let a time interval of t seconds be given. Suppose that an object travels a total distance of d feet during this time interval. The average speed of the object in the given time interval is the distance over that interval divided by the time for that interval. So the total distance divided by the total time gives us what's called the average speed. So here's an example. If car A travels 176 feet in 4 seconds, the average speed would come out to 44 because 176 divided by 4 is 44. What is the average speed of car A from 0 to 2 seconds? So the total distance from 0 to 2 seconds is 88 feet, and the time is 2. So the total distance, 88, divided by the total time, 2, would give us an average speed of 44 feet per second. Move car A to a different starting location and starting and ending points. Calculate the average speed of car A between the chosen locations. The total distance traveled here from 44 to 154 is 110, and the total time from 1 second to 3.5 seconds was 2.5 seconds. So 110 divided by 2.5 is 44. It says we found a rule for the function that describes car A. Can we use a function with the same rule to describe car B? Well, no, because it wasn't traveling at a constant speed. And it did not have a constant of 44 feet per second. Even if it was traveling at a constant speed, the constant speed did not match car A. What is the average speed of car B from 0 to 2 seconds? So from 0 to 44, that's a change of 44 feet in 2 seconds. 44 divided by 2 gives us an average speed of 22 feet per second. So it says move it to a new location. From 1.5 to 3 seconds, that's a time difference of 2 seconds. And from 24.75 to 134.75, that's a difference of 110 feet. 110 divided by 2 gives us an average speed of 55 feet per second over that time interval. Let's take a look at a graph of the data from car A and car B. How are the graphs similar and how are they different? Well, just noting, the axes are labeled with time and distance, so that's a similarity. Let's look for some differences. I see car A creates a straight diagonal line, but car B follows a curve. Do you think the distance the fish has dropped is a function of time? Well, as time is passing, the distance the fish has dropped is changing. So yes, I do think it is a function of time. Measure and record the distance the fish has dropped after each second. So at 0 seconds, it's dropped 0 feet. At 1 second, it still says that distance is 0. Never mind, I gotta measure. It has dropped 16 feet. In 2 seconds, it has dropped 64. In 3 seconds, the fish has dropped 144. And after 4 seconds, the fish has dropped 256 feet. Predict how far you think the fish has dropped at other moments in time. Well, from 0 to 1 second, it dropped 16. But then from 1 to 2 seconds, 64 minus 16 is a difference of 48. So it's increasing as it goes. So I don't want to just do half of 16 because it's picking up more distance over time. So after half of a second, it should be less than 8 feet so that the distance can increase over time. So I might predict that it is 6. Then it went 48 from 16 to 64. Well, half of 48 would be a change of 24, but we know that it's increasing as it goes, so I might only add 20. From 64 to 144, that was a change of 80. But in half a second, it should change less than 40. So I might add 30 to that, which would give me 94. From 256 to 144, it dropped another 112 feet. Well, half of 112 would be 56, but I might only add 50. So 144 plus 50 is 194. It shows my predictions for 3.5 seconds, 2.5 seconds, and a half of a second are incorrect. Oh, and 2.5 seconds. So I got 1.5 correct. So I'm going to leave that one, but I do need to adjust them if necessary. So I might bring this down to 5. This one I was too low, so I might bring that up to 95. This one, it looks like I was very close, so I might just adjust it by a little bit. I still need to fix a half a second. Let's try 4. 2.5 seconds. Let's try 97. And 3.5 seconds. Let's try 196. So now my half second is right. My 1.5 second is right. 2.5 still needs fixed. Let's try 98. Maybe 100. So now I have check marks all the way through. patterns do you notice, and does the fish drop at a constant speed? That increased by 4. From 4 to 16, that is a change of 12. From 16 to 36, that's a change of 20. From 36 to 64, that was a change of 28. From 64 to 100, that's a difference of 36. Here from 100 to 144 is 44. From 196 to 144, that was a change of 52. And from 196 to 256, that's a change of 60. It appears that it increases by 8 each time. That is what we call acceleration. So here, these are the speeds. If we were to divide by the time in seconds, but the change in the speed is called acceleration. So what pattern do you notice? The fish experiences acceleration since it's experiencing acceleration. The fish does not drop at a constant speed. Acceleration means that it's speeding up over time. Use the average speeds shown to make your answer more precise. So we see that it was 8 feet per second, 24 feet per second, 40 feet per second. So it's increasing as it goes up. How can we describe the function for the fish falling without an equation? We can look for other patterns in the table, just like we did with finding the pattern for acceleration. The distance the fish falls is increasing with each second. Because the fish's speed is increasing as it drops. What do you think the distance traveled after 2.75 seconds is? Explain. We know that it must be more than 100 feet and less than 144 feet because it is between 2.5 seconds and 3 seconds. We saw, if we were to break our table down further, that from 2.5 to 3, that was a change of 44. And from 100, nope, to 64, that was a change of 36. And we said our acceleration, 36 plus 8, made 44. So if we were to cut this in part and put a 2.75 here, we might expect our acceleration to be 4 if we're cutting it in half again. You may also notice that 4, 16, 36, 64, 100, 144, these are all squares. 2 squared is 4. 4 squared is 16. 6 squared is 36. 8 squared is 64. 10 squared is 100. 12 squared is 144. 14 squared is 196. And 16 squared is 256. So you might even consider that in between 2.5 and 3, in between 10 and 12 is 11. So maybe it's 11 squared, which would be 121. And 121 is between 100 and 144, so that's a possible solution. Basically, we're looking for patterns because we have been working with linear equations. However, this one doesn't follow a linear pattern. And so we need a different way to describe the function based on patterns from the table. Now at this point, we don't have a way to check or verify that that is correct. But in the future, we're going to learn other ways to describe patterns in both tables and graphs. What is the distance traveled after 0 seconds? That was 0 feet. What was the distance traveled after 5 seconds? From 3 to 4 seconds, 144 plus 112 makes 256. From 2 to 4 seconds, 64 plus 80 would give us 144. From 16 to 64, that was a change of 48. So each time, we wanted to go from 4 down to 5 seconds. Each time, these values are increasing by 32. So if we increase 112 by 32, that should be a change of 144. So if I add 144 to 256, that would give me 400 feet. If we follow that same pattern from before, this was 12 squared, and 256 was 16 squared. So 5 should be 20 squared, and 20 squared does equal 400. That is the end of lesson 1 for module 6. There will be more of those added to the playlist.